So let's see how geometric means show up, guess what, in geometry. This is the first place they show up. We're going to start with the right triangle. That's MTN here. And I'm picturing it with the hypotenuse at the bottom and horizontal, so we can think of it as the base of that triangle. But that's not crucial. We need to be able to do this with any orientation. This is a standard way to think about it to start. We're going to drop an altitude from that right angle at T to the hypotenuse. And notice what that does is it creates another internal right angle, really two right angles. So we've actually got three right triangles. We've got MTN, we've got MTR, and NTR. So that's three right triangles. And to make it really explicit, it's like make it an actual problem to solve, kind of a calculation that we'd like to do. Suppose that we know the whole hypotenuse is 25. That's what the 25 means. That's MN. And the two segments. So we've got MN equals 25, and we've got MR equals 16. And of course, the difference, RN, has to be the difference, which is 9. Okay, so 16 plus 9 has to equal 25. That's important. Okay, can we figure out the two legs? Can we figure out what MT is? And can we figure out what NT is? And could we figure out what that altitude that we dropped was with that TR? Okay, so that's that. I'll put that down here. That's what the altitude would be. Okay, well, here's the key thing. It's that not only are they three right triangles, they're not three random right triangles, they're all similar. So the key is that all three of the right triangles are similar. And literally, I could stop the video right now and you all could do the problem because you guys could figure out exactly how they're similar and then set up the proportions and then solve the problem. But it's cool to see exactly what kind of formulas you get out of this because it's really cool and it leads to literally the most famous formula in all of geometry that we'll get to very soon. So let's see why they're similar. So we've got angle TMR. That shows up both in the left-hand triangle and the original big triangle. So of course it's the same thing. It's the reflexivity property. It's the same thing. And so that's shared in the left triangle and the big triangle. Okay. And of course they're both right triangles too. We know that angle MTN, that's a 90 degrees. And we know that angle MRT is also 90. Okay, so we've got a similarity. Now we just have to be really careful. Let's see if it'll type it. Okay, so what's the similarity statement? Let's say the left-hand triangle has, we'll start with the M, and then we'll go to the right angle in the small triangle, which is R, and then we'll go to the other vertex, which is T. That's going to be similar. I wish we can't type. There we go. Is going to be similar to the big triangle, starting with that same angle M, then going to where the right angle is in the big triangle, and then going to the third. Okay. And so now we get a proportionality statement. Okay. So we get that TM, that's after all one of the things we want. I guess I'll call it MT. That's what I called it before. So MT is one of the things we wanted to find out before. MT, that's the hypotenuse of the left-hand triangle over that MR. Well, that's going to be the hypotenuse of the big triangle over, MT again. So this is the cool thing, that MT has a dual role here. It's the hypotenuse of the left-hand smaller right triangle, but it's also the leg, it's one of the legs of the big triangle, and it's one of the legs adjacent to angle M, which is shared. Okay, well, in the left-hand triangle, MR is the leg adjacent to angle M. That's why it's showing up here. And That's why MT is showing up in both these places. Okay, so let's put in the numbers. And we've got MT over 16 equals 25 over MT. So MT squared. And so, well, so I should say right now, this is where the geometric means come in. We've got exactly a geometric mean situation. MT squared is 25 times 16 is 400. Yes, I did contrive this to be super nice. In general, you're going to get roots at exactly this stage. I just wanted the very first example to be pretty numbers. So yes, we can totally figure that out. That's going to equal 20. Okay, very similar. We know that that angle TNR is shared in the right-hand triangle and the big triangle. Okay, and they both have a right angle. They're both right triangles. TRN, of course, is the right triangle. With the right angles at R in the small left-hand triangle. And of course, we know that in the big triangle, the right angle is at T. So our precise similarity statement, we'll probably have you pause and figure this out. So we're gonna go, let's say N from the shared angle to the right angle in the small one, oops, not a G, to the other one. That's gonna be from the shared angle to the big right angle to the other one. Okay, we are totally on a roll. The proportionality statement is now going to be Tn, that's another one of the legs of the original big triangle that we would like to find out, over Rn. Okay, so that's hypotenuse over leg that's adjacent to the shared angle. Then we'll just say the same words, but apply them to the big triangle. Hypotenuse of the big triangle, once again, Mn, over leg of the big triangle that's adjacent to shared angle N, and that's Tn. Yeah, that's another geometric mean statement. So Tn over, now it's 9 equals 25 over Tn, of course. Tn squared, we've got a geometric mean setup, that is 225. And yes, again, this is the contrived part. Generally, that's going to be some sort of root of a non-perfect square, but I chose it to have that be a perfect square. So far, so good. We've gotten MT and Tn. Let me pause it and put those in. Okay, there's one more. Well, there's a lot more that comes out of this picture. It's a really important picture. But we can also find TR, that altitude, the height of this triangle. And we can do that once again with similar triangles. So in the previous two, we used the fact that the left partial triangle was similar to the big one, and then the right partial was similar to the big one. Can we get anything useful out of saying, well, the left triangle is similar to the right triangle? And that's exactly where this is going to happen. What I claim is if you look at the left triangle, MRT, okay, that's this angle here, that M angle, that's complementary to the angle here, but they add up to 90, and so this angle here is equal to this angle. This is just another fact from the similar triangles. We could have derived that in all kinds of ways. That's just a double check that the angle at M here, RMT, is congruent to RTN. And similarly, RNT, that angle, that's complementary to this one, but that's in itself is complementary to this one, so we're back. So RNT is the same, that's congruent to RTM. So just confirming something we already knew, that these are all similar to each other. And so, for example, this angle corresponds to this one. The reason I did that again carefully is to make sure we're really doing the right angle corresponding to the right angle. So M in the left-hand triangle corresponds to T in the right-hand. Ooh, still need my triangle here. And then R, of course, in the left-hand triangle corresponds to the right angle in the right-hand triangle. That's R again. And then, of course, it's going to be TRN. Right? So the angle at T, MTR, as we said, is congruent to T and R, and that's what gets this guy. You really have to just go through slowly, carefully, and convince yourself that you're not getting it messed up. Okay, and therefore, what can we say? We want something about TR, and we hope that we get something where TR shows up twice. Well, TR over MR, that is the leg opposite M in the left-hand triangle over the leg adjacent to M. Well, what does that correspond to over here? Remember, this angle here corresponds to the angle here at T. So now we're going to do opposite to that guy. That's a 9. We're going to put that in a second. Over, yay, TR. Okay. So this one you can picture, just take that MRT triangle and try to visualize rotating it 90 degrees around the pivot of R and shrinking it down to fit here. That might help as a visualization. Okay, we are so close. Almost done with this video. MR is known to be 16. And RN is known to be 9. And we've got another geometric mean statement. And again, I did contrive this to everything be nice. It's rather rare. Just kidding. That everything's going to be an integer. But it turns out TR equals 12. And what did we discover? It's the geometric mean of just the 16 and the 9. All right. So let me summarize real quick what we found. I wanted to do it with just really explicit numbers. We can summarize that that left hand leg of the big triangle is the geometric mean of the whole hypotenuse and the left hand segment of the hypotenuse. And of course the book, it's their job to summarize this as well. Hypotenuse. Okay. And guess what I'm about to write? Down here, I'm just going to say the same thing with right. So not exactly super hard to predict. All right. So that 15 we ended up getting as the geometric mean of 25 and 9. Okay. And then the altitude of the original triangle, that's even kind of more elegant. It's the geometric mean of the two segments of the hypotenuse. So that's kind of symmetrical. The altitude doesn't really have a preference for left or right-hand triangles. It's between them. So it kind of has to use some sort of symmetrical information. And it's very elegant that it's actually just the geometric mean of that left-hand part of the hypotenuse and the right-hand part of the hypotenuse. There are definitely more equations you can get out of this, including, as I said, something super famous just coming right over the horizon.